Okay, so first of all, I would like to thank you for the invitation. It's always a pleasure to go here in New York. So I am going to talk to you about the concatenation of several work of transcendence of a special function. So every time I will write a theorem, I will say who is the cause and so on. First of all, I will define what is a differential transcendence. So let f be a function. So it's a function that belongs to a differential field. We say that f is differentially algebraic if and only if there exists an integer n, which can be 0. There exists a non-zero polynomial in n variables, in n plus 1 variables, such that the polynomial vanish the derivative of f. So in other words, f and its derivative are algebraic independent over C. And we say that f is differentially transcendent otherwise.
Did you want to do C or something okay?
In the talk it will be C, so in general it can be K, but in the talk every time the field of constants will be C. But C can be replaced by any field.
And
because it's differentially algebraic over C.
And by replacing C by K?
Everything will go. You just need that f belongs to a differential field, and this is a subfield of this differential field.
One derivation?
Yeah, one derivation. You can consider the situation of several derivations, but in this talk I will be interested in only one derivation. And the goal is to give criterion that ensure that f is differentially transcendent. So in general, it's a complicated task because if I consider a formal power series and if I ask if it's solution of a linear differential equation, then there are plenty of algorithms with a guessing method that give you an idea of if it's solution or not of a linear differential equation. For the algebraic differential case, it's much more complicated. So we have to restrict the framework, and we are going to consider the situation where f is solution of a difference equation. And in this framework, we have the powerful tool of the difference Galois theorem. So let me be a little more precise, and let me give the exact framework. So I consider the following triples, so it's K, sigma, and delta. So K is a field of characteristic 0. Sigma is an automorphism. And delta is a derivation. So it's a field equipped with an automorphism and a derivation. And I consider field extension on this field. So f will belong to this field. And consider a non-zero function such that its solution of a difference equation. So the equation has coefficient in k, and we assume that it's a real equation, meaning that if you consider the product A0, N1 is non-zero. Otherwise, you have an equation of smaller order. And since sigma is an automorphism, you may always reduce to a situation where A0 is not zero. So we are interested to know if f is solution of an algebraic differential equation, and I'm going to give you one more motivation to consider this problem. If you are able to prove that f is differentially transcendent, then it means that f is algebraically independent to any differentially algebraic function. So its basic properties on differential algebra. And so, for instance, we are able to prove that the gamma function is differentially transcendent, and then it's proved you that the gamma function is algebraically independent to the exponential or to the Weierstrass function. So, being able to prove that one function is not solution of an algebraic differential equation gives you the algebraic independence to a lot of functions. So, we are going to make some extra assumption. I'm going to assume that the automorphism and the derivation are commuting. I'm going to consider the field of constants. So this is the element of K that are invariant under the automorphism. And I am going to assume that it's algebraically closed. So typically, this field will be the field of complex number. And I'm going to assume that K is a C1 field. So it's a technical assumption. I'm not going to recall what is a C1 field, but every field that you want to consider in real life are C1 fields. So rational function from hyperbola series, most of the fields are C1 field. And a last assumption, which is not neutral. So if you consider a finite field extension such that sigma extends to L, then L equals K. So you have not non-trivial algebraic extensions that are stable under sigma. So now I'm going to give you some example.
Can you say some? I missed what you said about the last condition. Can you
I say that if you have a finite field extension such that phi extends to it,
okay,
then it's the ground field.
Okay, I see.
So I may give you the following example. So K can be the shift case. So K can be C of X. Sigma is the map f of X to f of X plus 1. Okay. Delta is a classical derivative. And you can take for F the field of homomorphic function over C. There is Q difference cases. So f of X maps to f of Qx with Q complex number with modulus difference than 1. This time the derivation is a little more complicated, but you can prove that something is differential algebraic for this derivation if and only if this is the case for this one. And if you want that this condition is satisfied, then you have to ramify the field. So you have to take the ramification of L, because the square of x is a solution of a Q-difference equation. And the field where F belongs this time will be the field of formal P the series. There is also the Malayan case. So f of x maps to f of x to the p. So this time if you want a derivation that commutes, it's a little more complicated. You have to add the logarithm. You can check that the automorphism and this derivation commutes, but since the logarithm is differential algebraic, it's the same property as this one, so it's okay. And so the ground field here, I need to add the logarithm in the ground field. But everything is fine because this function is transcendental over the ground field. So you can add it, it will not give you a lot of problem. And to finish, there is the elliptic situation. So this is the field of function. So I'm going to write the elliptic function in the multiplicative way. So this is the field of functions that are homomorphic on C star and that are P invariant. It's invariant under the multiplication by P, and the automorphism will be the following one with Q different than 1, and again we have the inclusion of field. So this is the 4 main example where we are interested.
Excuse me,
Stop here.
I can't quite read what the set of all F in what?
Here, it's
No, down in E, the elliptic case.
It's a Q. It's
No, over there. Set of all F in.
Here.
The set of all.
F is a homomorphic function on C star.
Oh, mere. Oh, whoops. Thanks.
Sorry. It's a homomorphic function on C stars that is P invariant.
Can I ask one question? So the last condition on the left,
Yeah.
is it easy to see why that's true? For instance, in the first example in S that you give, or not?
For the first example, it's a theorem. So
Okay.
Van der Poot and Singer usually consider this case, and they prove a theorem that says that in this situation. So it's not trivial.
Okay. And when you say extend for a finite field extension, do you mean in such a way that sigma still commutes with? Oh, okay. Now I understand.
Yeah.
Okay. Now.
So now I'm going to tell you a little about Galois theory. So I know that a lot of people are very friendly with this theory, but let me give a few words on it. So I remind that we have a difference equation of the following form, and we always prefer to see that as a system. So you have a companion matrix on the following form that we call A, big A. So we are interested about knowing what are the differential equations satisfied by a solution of a linear differential equation. So the first paper that deal with this problem was the Galois theory of Philip Cassidy and Michael Singer. In these situations, they were considering linear differential equation depending upon parameter, and they were trying to know whether the solution was solution of an algebraic differential equation for the differential operator. And then this Galois theory has been generalized by Ardouin and Singer, and they consider this situation of a field equipped with a derivation and an automorphism, a function solution of a functional equation for the automorphism, and they were asking if it's solution of an algebraic differential equation for the other operator. But in the same way as in Cassidy-Singer theorem, we need to consider one field which is differentially closed. So you can avoid this kind of strategy using Tanaka categories as shown Alexei. But I prefer here to sketch to this very straightforward way. So differential closed field is a very big field where you are able to solve every algebraic differential equation that can be solved. So we consider the field of fraction of K tensor this field over C. So it's still a differential field, and its field of constants is C tilde. So this field is sufficiently big to answer you that you are able to use the theory of Alder-Singer. So a sigma delta Picard ratio extension is a sigma delta ring extension R tilde over K tilde. L tilde, sorry, over K tilde, such that you have the existence of a fundamental matrix of solution having coefficient in L tilde. So you are able to solve your equation in L tilde. L tilde generated by U, the inverse generated over K tilde, by U, the inverse of the determinant and the derivative. And the last assumption is that the sigma delta ideals of L tilde are 0 and R tilde. And the last assumption implies that the field of constants of L tilde is C tilde. So it's not going. So following the proof of Cassidy-Singer, Ardouin and Singer proves that there exists a unique Picard ratio extension. So everything works, and now we are able to define the Galois group. So the sigma delta Galois group. This is so the automorphism of L tilde that leave K tilde invariant such that you commute with the automorphism and the derivation. And so we can take delta equals 0, so delta is a trivial derivation.
So by the way, so what you're talking about, is this a setup to explain your proof, or is this a setup that you will use even to state the main result?
I will basically use this for the proof at the end.
But this is not needed to state your main result.
Yeah. More or less.
Because this is just one can use, it's just some technical thing that
Yeah.
you choose to use. Okay.
Yeah. And so you may also take delta to be 0, so you are in the framework of the classical difference gamma theory. And so in this situation, you have a Picard-Vissou extension. And in this situation, you commute as well.
But you won't give a proof, right?
I will give a sketch of proof.
Okay, so that's why you're talking about this.
I will give you a sketch of proof of everything. So theorem. So you have an embedding of the Galois group into a group of matrices, and to psi. You map u minus 1 psi of u, so if you apply sigma to it, you find that it's invariant, so you fall into the Gaussian of C tilde. And so it's a differential algebraic group, so it means that it's a group J such that there exists P1 pk polynomial in n square variable such that a matrix B is in J if and only if the entries are satisfying some algebraic differential equation. So I may give example of the following situation. For instance, so if you consider SL2 of C tilde, it's the matrix that is an algebraic equation, so it's an algebraic group, so it's a differential algebraic group. But you may also consider a non-trivial one. So for instance, you can ask that the derivative are vanishing. So it's a group, it's a differential algebraic group. And we have a relation between the two Galois groups. So the differential difference Galois group is Zariski-Jones in the classical Galois group. But since the Galois group will be an algebraic group defined under C, you have to consider the C tilde point. And the second one is that the dimension of the Picard-Vissou extension corresponds to the dimension of the Galois. So bigger is your group, and a less algebraic differential relation you have among the solutions. So for instance, if you have these groups, it means that you have three, so the dimension is 3, so you have 3 solutions that are algebraically differentially independent. Here, if your group is this one, then you have 0. So it means that every solution will be differentially algebraic. So now I'm going to state some result. So I'm going to give you a general criterion to ensure that F is differentially transcendent. So it's a joint work with Carlos Arreche. And Jean Roch. So originally, the main motivation of this work was the study of the elliptic analog of the hypergeometry functions. It has been studied by many physics people. And one of them asked us if this function were differential algebraic or not. And the problem is that we realized that the equations were extremely complicated to handle, so we need to state a criterion that was as general and was as easy to state. So, from now I'm going to assume that n equals 2. Let me rewrite the equation. So let me call the coefficient a and b, and f is still an element of the field extension. And so our theorem states the following. We are going to assume the two following things.
Excuse me for a minute. Could you read the equation?
Just
I can't read it.
A sigma f
Can
plus b.
Yeah.
write it again.
Yeah,
So it's
thanks.
sigma 2 of f plus a sigma of f plus b times f equals 0. So it's just another two equation, and I just call a and b the two coefficients.
And what do you mean by dimension of L tilde or K tilde? Of the fields?
So
Transcendence degree or?
yeah, transcendence degree.
Is it differential transcendence degree
Yeah.
or zero? Yeah,
Zero.
for
Yeah.
such things.
So L tilde is a priori a direct sum of integral domains,
Okay.
and so it's
Yeah.
maximum the dimension of
Transcendence
integral.
degree.
It's kind of hard to give a precise statement of what does it mean. It takes one page of definition, but it's what you believe.
Yeah, yeah.
So I'm going to assume two facts. I'm going to assume that the Riccati equation so the following Riccati equation has no solution. In the ground field. So just after I will explain you what is the link with that and differential Galois theory. And there are no C0 until Cn in the ground field C, in the constant field C with C0, Cn not 0. Not R0. So there are not complex numbers, not R0, and H in the field K, such that the sum, the following sum, so it's the sum of Ci and the E time derivative of delta B to the B equals sigma H minus H. I will make a comment in a few seconds. So, and in if these two assumptions are satisfied, then F is differentially transcendental over K. So, let me make a few comments. So, in many situations exist algorithms to test if the Riccati equation has a solution or not in the ground field. So, in the shift or the Q-difference case, we are able to test this, and the elliptic case as well. And this kind of equation is known as the telescoper equation. So many people, like Shen and Singer, used to study this kind of equation and prove in which situation you have or you don't have solution. So you have criterion based on the residues of B. So depending on the residues of B, that say if it exists or if it does not exist.
Is 2 equivalent to your conclusion?
No, it's an implication. So I don't claim that if F is differentially transformed, then those two assumptions are satisfied.
If one is satisfied, is 2
No,
equivalent?
if the two are satisfied, then it's differentially transformed.
Okay, if one is satisfied, is 2 equivalent to your conclusion?
No, you need the two assumptions. Assume that the Riccati has no solution and there is no telescoper, then there is an end between 1 and 2. Then F is differentially transformed.
Again, do you have an example? When one is satisfied, your conclusion is satisfied, but 2 is not satisfied.
There should be a lot a priori. Should be a lot of them.
Yes. If you really consider n equals 2, they may have not so many counterexamples, but if you consider n bigger than 2, yes. I believe that in some situations the first assumption will be sufficient.
So you're assuming that difference equation,
Yeah.
and F is a solution of that equation. What is the Riccati equation associated with that difference equation? Oh, what?
It's this Riccati equation.
This is the equation. That's the equation that he's pointing to.
Yeah.
I can't read that, I'm sorry.
Sorry, I can rewrite.
I should move over, I think.
It's sigma u plus A times u equals minus B.
Oh,
And
okay. Okay.
it's
Sigma
exactly-
u equals A.
Yeah, it's exactly the same as the differential case. It's more or less equivalent to the fact that there is a solution of this equation that is a solution of order 1 equation.
Ah, not logarithmic.
No, if you have
Sigma u equals A.
if you have y, which is solution of an order 1 equation, and solution of this order 2 equation, okay, then you may check that this relation is satisfied. Because you replace sigma y by uy and sigma 2y by sigma u times u. Right? You divide by u and then you find. So it's just equivalent to the fact that to have an order 1 solution. And so this criterion was sufficient to prove that in many situations the elliptic analogous of the hypergeometric function is differentiated also. So now I'm going to give you a sketch of proof. So the first condition implies that the Galois group is irreducible. So, under the assumption I made in the beginning, there is a theorem of Vanderput and Singer that says that you may perform a Gauss transformation that put your system into the difference Galois group. And in fact, we can prove that.
What's the meaning of irreducible?
It's not contained in a group of matrices of this form.
Oh, right, thanks.
So the group is not conjugated to a triangular group.
Yeah, it's not a topological condition. Or maybe it is.
So we have a classification of algebraic group of LGL2, and in fact, we have that the Galois group is either a subgroup of the infinite Galois group. So it's the group of the following form. Okay. Or the Galois group contains SL2. So the Galois group is not conjugated to a triangular group, so it's conjugated to a subgroup of the infinite Galois group, or it's big, it's contained SL2. And the second assumption we made was give us an information on the determinant. The second information implies that the determinant of the sigma delta Galois group. So it's a subgroup. Its Galois group is the group given by the determinant of the matrix. So it's a sigma of y equals b of y. And in fact, we have that this determinant is maxima. So if you consider the determinant of the image of the sigma delta Galois group, you have no relation. And now we have a theorem of classification of differential algebraic group, and if we put together, we find that we have only two possibilities for the Galois group. It's either the entire Galois group, or it's GL2. So this group has dimension 2, and this group has dimension 4. And each of the two possible situations, the dimension of the group is sufficiently big to answer you that every solution of this equation are differential isomorphic. So here the assumptions are here to answer you that the Galois group is sufficiently big. Any question on this? So I told you that we apply this for the elliptic analogous of the hypergeometric function. So there are different equations of an elliptic curve of dimension 2. There are solutions of that depend upon many parameters, and we prove that under a specific choice, generic choice of the parameters, then these two assumptions was satisfied. And to finish, I will tell you about another work, which is a work in progress. And this work is valid only in the case shift, difference, and malware. So it's a joint work with Boris Adamczewski and Charles Tarpin. as well for some part. I'm going to assume, I'm going to give an example. So I'm going to assume that the sigma Galois group
This is the joint work of you with them.
yeah.
Okay.
There is one joint work with me and them, and there is one joint work with me and them. So it's two different groups. So I'm going to assume that the sigma Galois group is SF2. And then I told you that the parametrous Galois group is Zariski dense in SL2, okay? So we have a differential algebraic group, which is a Zariski dense subgroup of SL2. And so a priori it's a complicated task to know what it is. But if you ask to Phyllis Cassidy, she will tell you that she made a classification of such a Zariski dense subgroup, and there are only two possibilities. So the Galois group is either SL2 of Cetil or SL2 of Cetil of points that are zero derivatives. It was two groups that I've written before. So you have only two possibilities. So this one, as you mentioned, 3, and this one, as you mentioned, 0. So if your group is this one, then every solution will be a priori differential algebraic. If your group is this one, then every solution will be a priori differential transcendent. So we want a way to say that this cannot really happen, but it does not happen. So how? I'll show you that this does not happen. If you look carefully, you have a theorem of Galois theory that says that the Galois group is SL2 of C tilde if and only if there exists a fundamental matrix solution which will be solution of the two matrices of two systems with B, a matrix having coefficient in K. Okay? So the Galois group is small if and only if you have a fundamental solution, which is solution of the both equation. And if you look at this condition in an algebraic way, you say, okay, so it's equivalent to with the commutation of sigma and delta, it's equivalent to a certain Lax pair condition, so you have to check if it's correct or not. But if you look it in the analytic way, it's much more stronger. Because if you consider a formal series, which is solution of a difference equation, there is a priori no reason that it will be solution of a differential equation. And in fact, you have a theorem, for instance, for Rami that says that if you have if a formal series is solution of a Q-difference equation and a differential equation, then it's a rational function. You have a result of Bézivain that say more or less the same thing in the Marian context. So I'm going to make the following hypothesis, which will be satisfied in the three cases that interest us. So I'm going to assume that if F is solution of sigma in an equation in coefficient in K and a delta in an equation in coefficient in K, then F belongs to the ground field. So this is the situation for the case Q and M, and if you want, it could be the situation for the shift case. You have to define the ground field a little more carefully than I did, but you have this same kind of result.
You're assuming this situation, SL2, etc.,
Yeah.
with this statement over here?
No,
Or in
this is the
general?
end of the example. So it was a motivation.
Is this for in any situation?
Yeah,
not
in
just-
any situation, I just assume that we are in this situation. So we have.
Okay.
So I just make an extra assumption that says that if function in the field F is solution of a difference equation and a differential equation, then it belongs to the ground field.
Yeah.
And it's the situation for the Q difference case as the Malloyan case that I stated before. Okay? So for the shift case, it's a little more complicated because you have the exponential, which is solution of a shift equation and a differential equation. But for the Q difference and Malloyan, if you consider formal series, and it will work. So if I make this assumption, we see that this group cannot occur. This group doesn't exist.
Mm-hmm.
So we will automatically have this kind of group. So if the sigma group is SL2 in this situation, then that differential Galois group will be sufficiently big. And we can go further. So it's a previous work, so it's a concatenation of two work with Charlotte Hardouin and Julian Roch. So in case Q and M, if the sigma Galois group contains SLN, then any non-zero solution is differentially consonant. So we still have our equation. So this time it's not n equals to it for general M. So if you are able to prove that the Galois group contains SLN, then the non-zero solution are differentially consonant. And I should mention that the case S has been treated by Carlos Areche and Michael Singer. So it's a general criterion. If you are able to prove that the difference Galois group is big, then any differential algebraic equation, any solution is differentially transcendental. In the case Q, we also consider the situation where the base field is equipped with two automorphisms. So basically, we have sigma Q1 and sigma Q2, with Q1 and Q2 independent. And then we have a Galois theory by Alexei Ovchinnikov and Michael Wigmer and show you that a solution of this kind of equation is solution of an algebraic functional equation for the other operator or not. And we are still able to prove this kind of result in this double Q context. And to finish, we'll mention one of the results that we have with Boris And let me make a last comment. So, in the Malayan situation, this kind of result has one more advantage, because there is a whole community of people that are interested about knowing what are the algebraic differential relations satisfied by the solution of Malloy equation. So the approach was, how to say it? But there were one equation, one paper, one equation, one paper, and this kind of result allow you to give a general criterion that may be applied to several equations. So, and if you consider n equals 2, then this assumption can be tested algorithmically. If you consider more than n equals 2, it's more complicated. And why people of this community were interested about the Malayan situation? So Malloy functions are linked with automatic sequences. So if you consider real number, you want to understand what is the complexity of the writing of this complex number, of this real number. And they invented a class of number which called the automatic numbers that can be, with digit, can be expressed with an automatic sequences. So, roughly speaking, it means that the digit may be algorithmically computed with a computer. And so, to the automatic numbers, they associate the corresponding geometric series, which will be solution of a Malloy equation, if and only if the function is automatic. And the main goal is that the Malloy function have a lot of properties. So, for instance, we know that if a Malloy function is algebraic, then it's a rational function. So, there are a lot of properties of Malloy function. And there is a very beautiful theorem by Philippon that says that if the Malloy function is transcendental, then its value at algebraic point are also transcendental. And it's extremely powerful because proving that a function is algebraic or transcendental, you can do it in many situations. It's not so complicated. You have the Galois theory that allow you to do a lot of things. But proving that a given real number is transcendental or algebraic is extremely complicated. We have very few examples. And it was the reason of the motivation of those people to understand the transcendence or not of Malloy function. It was to just have a bunch of examples of a transcendental number. So,
A real question.
Yeah?
What would be the main reason for you to talk about this at the end rather than at the beginning of the talk?
Because I forgot it. I would say I would have preferred to say it, to say a few sentences at the beginning of the talk, but I just remember in the middle of the talk that I want to say that, so I take advantage of this few minutes to say it.
And so you mentioned something really exciting about the Malloy case. What about the other cases? Are they also connected to something exciting?
Not in my knowledge. I know that many people study pure-difference equation, so they are linked with a lot of things coming from physics, for instance. And I don't know if there is another special reason to study. But so it was the reason why our first paper was on Malloy case, because there were a motivation, and then we realized that our technique could be also applied for the equation. So we just generalized. So to finish, I will going to give you. So the A here is Adamczewski and not Arashi anymore. So let F solution of another two equations. So F is solution of this other two equation. and the following dichotomy holds. F is a rational function, belongs to the one field, or F is differentially transcendental. So it's under this assumption. So basically, for under two equations, it means that the only differential algebraic equation you can find it's linear differential equation, and with this assumption, then they automatically belong to the ground field. So it means that for n equals 2, very few things may occur. You belong to the ground field, or you are differential transcendent. So to prove that a function is differential transcendent, it's just suffice to prove that it's not a rational function. So if you replace the field of formal power series by something else, it's not true anymore. So for instance, if you consider this equation, so f of x equals x times f of x, so you have a theta function which is solution of this equation, and we can prove that it's solution of a non-trivial differential algebraic equation. So it's not always the case that you have this kind of treatment. So this is a theorem that works for the n equals 2 case. We believe that it's true for any n, but we have no clue of any proof of this statement. So it's a conjecture. It's conjecture that formal power series is rational or is differential transcendent. But this kind of result would be the last step of the study of the differential transcendence of a special function. So I hope that this talk has given an overview of what are the kind of questions we are interested in, what kind of application we have, and I would like to thank you for your attention.
I notice in all of this you start as a kind of base field, the field of complex numbers.
Yeah.
Are your proofs purely algebraic, or do you use analysis?
It depends. I mean that...
I'll change that.
You can say that this assumption, you can say it's an analytic assumption, and prove that it's satisfied in the Q-difference case or in the Malheur case is analysis. So the original proof were analysis, and then there is a paper of Michael Singer and Reinhard Schafke.
What was the second name?
Reinhard Schafke from Strasbourg. Schafke. I will probably misspell it, so I apologize. It's something like that.
Oh, no. Yeah.
And
they
French. Prove it's German.
Yeah, no.
They prove this kind of statement uniformly, and their techniques are much more algebraic. But there is still an analytic part.
Yeah, okay. I have another question. What about generalizing this program to parametrized differential equations to get a function, say a special function like the incomplete, you're going to think this is my only special function, the incomplete gamma function, two independent variables, satisfies a linear differential equation with respect to one of them, and no differential equation, pure differential equation with respect to the other. But it also satisfies a difference equation, of course, gotten from the special case of one variable. So I would think this theory would generalize easily to that parametrized situation. And I wonder if the same sort of theorems would hold.
So you mean that your function is solution of a linear differential equation?
Yes.
you have a differential parameter of operator
Right.
and a difference.
And a difference, linear difference equation or a Q equation, whatever. Any kind of difference equation.
So you mean
And don't ask me what it is
You
for the
have-
gamma function
you have a
in the
function of
partial
this
case.
form, okay?
Yeah,
And your field is equipped with this derivation
yes,
and another derivation
yes,
and another divisor.
yeah, all three. And
You want to
they
understand the relation
commute,
with
they
this?
commute, then they do commute. In this case of the gamma function, sigma commutes with both delta,
Mhm.
delta t and delta x.
So sigma is the shift?
And it's a generalization.
I guess it
from-
depends upon x and t, something like that?
When you generalize to the incomplete case, it changes a little. Basically, yeah, basically.
And so it's a
Yeah.
t derivation and
Yeah.
x derivation? Okay.
Yeah, and I'm assuming you then have a Galois group. It satisfies the correct conditions. And I was just wondering what the nature of the Galois group would be. It probably goes way down. It could be the case that, yeah,
So,
the group isn't very interesting, but
I may have two comments. So the first one is that when you consider difference equations, this kind of strategy is quite powerful because you have this kind of assumption. So being solution of a difference and differential equation is extremely stronger. Being
Yes.
solution of two
Yeah,
difference
yeah.
equation is stronger. Being solution of two differential equation is quite low. There are a lot of functions that are solution of,
right.
for instance, exponential of
So you
tx.
suspect the same thing would hold.
Exponential of tx, for instance, is solution of both equations. So
It can't because incomplete gamma is certainly not in the ground field.
and the second potential problem is that so when you add an automorphism as a parameter, so it's a theory from Alexei and Mikhail for two automorphism and Dividio, Ardouin and Wimmer for
Right.
one derivation and one automorphism. And the techniques are much more tricky.
Yeah.
So it's not like in Ardouin singular theory where you can consider any number of derivation, any number of parameters.
Right.
Here they just consider the situation with one derivation, one parameter. And when I ask them why, they said that it's extremely complicated.
Oh, okay.
So maybe the theory can be built on this example. Maybe on one example you can do something, but it will not be free.
Yeah. Okay.
It will be a lot of work. But if you give me the equation, I can...
Okay. Yeah, I will. Yeah. I haven't thought about it in a while. Very interesting. Do you have any notes written up?
So for the paper with Carlos Areche and Julia Rock, it's an archive.
Which one? Sorry.
The first I mentioned for the other two equations and the general criterion. That say
okay.
that's a no Riccati and
So-
no telescoper. It's on archive.
Will your
This one
website?
are on archive too.
Oh, okay. Your website have references?
Yeah, and this
okay.
one is published, so
Yeah.
it's a final version. This one is under review,
Okay.
and this one is it's under construction.
Good, thanks. Yeah, it's very nice.
But I hope in a few months it will be complete.
Very nice.
More questions?
Thank you.
Okay, that's it. Thank you.
Welcome.